Welcome to part 3 of this video playlist about the preparation of pyridines. This video is about the acylation of pyridines by substitution of hydrogen. Pyridines are too electron deficient and cannot usually be acylated by Friedel-Crafts acylation. Also, acylation first occurs at nitrogen to yield a still more electron deficient pyridinium salt. There are, however, some alternative strategies for the preparation of pyridyl ketones. One is the nucleophilic acylation with acyl radicals. These reactions usually require acidic conditions to enhance the electrophilicity of the pyridine. Acyl radicals are nucleophilic radicals which tend to add to pyridinium salts at positions 2 or 4. As indicated in the sketch, an oxidant is required for the final aromatization. Acyl radicals can be generated by oxidation of aldehydes or acetals or from various derivatives of carboxylic acids. These radicals tend to fragment into carbon monoxide and alkyl radicals, and alkyl pyridines are therefore common byproducts of these reactions. Another strategy is metallation with a strong base, followed by treatment with an acyl halide or ester, or with carbon monoxide and an alkyl halide. As discussed in part 2 of this playlist, pyridines can sometimes even be metallated at room temperature and with alkoxides or sodium hydroxide. Direct electrophilic acylations only work well with donor-substituted pyridines or intramolecularly. One reason why Friedel-Crafts acylation only rarely is applicable to pyridines is that both the Lewis acid and the acyl halide convert pyridines into pyridinium salts. As shown here, phosgene reacts reversibly with pyridine to yield a pyridinium salt, but no products of acylation at carbon. 2 and 4 alkyl pyridines may also be acylated at the alkyl group, as in this example. Thus, some alternatives are needed to acylate pyridines. I'll show you now some specific examples of pyridine acylations, beginning with the nucleophilic addition of acyl radicals. Here, ethyl-4-picolinate was acetylated by treatment with paraldehyde, the trimer of acetaldehyde, and with terz-butyl hydroperoxide. 1 equivalent of trifluoroacetic acid and 2% of iron sulfate were also needed. Along with the monoacetylated pyridine, a small amount of diacetyl byproduct was formed as well. Yields of these reactions tend to be moderate only, but reagents and catalysts are often inexpensive. This reaction probably proceeded by the radical chain mechanism sketched here. A terz-butoxyl radical, formed by iron-catalyzed homolytic cleavage of the hydroperoxide, would abstract hydrogen from the acetal. The resulting dialkoxyethyl radical would then add to the pyridinium salt to yield a radical cation. This would reduce the hydroperoxide and generate a new terz-butoxyl radical and the alkylated pyridinium salt. This is another example of pyridine acetylation. Again, terz-butyl hydroperoxide, a carboxylic acid, and iron catalysis were used, but instead of paraldehyde, triethyl orthoformate was the precursor of the acetyl group. The ethoxy groups were probably first oxidized to acetaldehyde and then to the required acetyl radical, as sketched here. By the way, when formulating a potential mechanism for such radical chain reactions, pathways that require the combination of 2 radicals are highly unlikely and should be avoided. During such reactions, only low concentrations of radicals are usually attained, and these will immediately react with components present in substantial amounts in the reaction mixture, but not with other radicals. Their concentration is just too low. Here, pyridine was benzoylated with benzyl alcohol and potassium persulfate. The reaction proceeded in water and without any acid, and it is unclear whether a hydroxybenzyl radical or a benzoyl radical added to pyridine. Anyway, the ketone was obtained in high yield with a moderate excess of reagents only. Alkoxycarbonyl radicals can be generated from pyruvates and hydrogen peroxide. Unfortunately, this radical added to 3-cyanopyridine with low regioselectivity only, and a useless mixture of products resulted. But this does not always have to be so. The addition of an aminocarbonyl radical to pyridine, for instance, proceeded with high regioselectivity. This radical was generated from formamide by oxidation with potassium persulfate. Aminocarbonyl radicals can also be generated from isonitriles, as shown here. Unfortunately, a rather high reaction temperature was required, but both with 4-picoline and 2-methoxypyridine, mainly one product could be isolated in acceptable yield. Another strategy to acylate pyridines is by metallation and then treatment with some carboxylic acid derivative. Unfortunately, these reactions often require very low temperatures that are difficult to attain in large industrial reactors. At 0 degrees Celsius, however, pyridine metallation does not always proceed as expected. For example, when 3-picoline was treated with LDA at 0 degrees Celsius and then with a chlorosilane, no silylation of the pyridine ring occurred. And butyllithium at 0 degrees Celsius mostly added to the pyridine ring. One superior strategy is metallation in the presence of dimethylaminoethanol, as shown here. In this example, only the acylation was carried out at low temperature and a fair yield of pyridyl ketone was obtained. Also, lithiated tetramethylpiperidine can metallate pyridines at room temperature. Here, lithiation of 2-chloropyridine at position 3 followed by acylation with benzoyl chloride gave an excellent yield of 2-chloro-3-benzoylpyridine. Interestingly, position 6 of 2-chloropyridine can be lithiated and acylated in high yield by using another base and no copper chloride. 2-fluoropyridines readily undergo aromatic nucleophilic substitution, and lithiated 2-fluoropyridines tend to oligomerize upon warming to room temperature. In this example, 2,6-difluoropyridine was metallated with LDA at -75 degrees Celsius and then formylated with DMF. The workup was critical for the outcome, though. If the reaction was quenched with water instead of hydrochloric acid, the main products were dimethylaminopyridines. Ideally, such reactions should be worked up by pouring the reaction mixture into an excess of dilute aqueous acid so that no free dimethylamine can be formed at any time. This is an example of directed metallation of a nicotine amide with lithium tetramethylpiperidite, followed by acylation with a benzamide. Mostly one isomer was obtained. In this interesting example, again a directed metallation was achieved, this time with sodium hydride. An intramolecular migration of the aminocarbonyl group ensued, followed by reduction to an aldehyde with the excess sodium hydride. The sodium iodide was probably required to increase the solubility of sodium hydride. This is an example of pyridine acylation with carbon monoxide and a terminal alkene. As catalyst, a small amount of ruthenium carbonyl was used. Lithiated pyridines are highly reactive, what can cause the formation of various byproducts. I had already mentioned the nucleophilic addition of butyllithium to pyridine. Other potential side reactions include dehydrohalogenation and oxidative dimerization, as in this example. In part 5, I'll show you a number of examples of the oxidative dimerization of metallated pyridines. Thus, acylation of pyridines with acyl radicals or by metallation may work, but the regioselectivity can be difficult to predict correctly. Let's have a look at some other acylation strategies. This here is a rare example of a true electrophilic acylation of a pyridine. It certainly helped that the reaction was intramolecular, because cyclizations yielding 3, 5 and 6-membered rings proceed much faster than similar intermolecular reactions. Alkoxy and aminopyridines are more electron-rich than simple alkyl or halopyridines and can often be acylated by electrophilic acylating reagents. In such reactions, the regioselectivity is usually determined by the electron-donating substituent, as in this example. Here, 2,6-dimethoxypyridine was acylated by an anhydride and an excess of titanium tetrachloride. With 4-methoxypyridine or 2,4-dimethoxypyridine, however, this acylation did not yield any ketone. Aminopyridines are easy to acylate ortho or para to the amino group. This here is an example of intramolecular acylation of an aminopyridine. Such reactions often give high yields, and many examples have been reported. Here are some further examples which you can also find in the description of this video. The next video of this playlist is about the alkylation and vinylation of pyridines. There you can find examples of nucleophilic additions to pyridines, of the addition of alkyl radicals, and of the reaction of metallated pyridines with alkenes, alkynes, and other carbon electrophiles. See you then.